Let's begin with the question majority element 2. The question is saying that you are given an array ARR consisting of n integers where each number represents a vote to a candidate. Return the candidates that have votes greater than n by 3. If there is not a majority vote, then return empty array. And one note is mentioned here that the answer should be returned in an increasing format. What does the question say? The question is saying that you would be given an array, okay, and it would have some elements. Let's suppose these are the elements. Well, do we need to care about the magnitude of these elements? Well, actually not, because we are just talking about number of occurrences, aka in this case, which is being referred as votes. Okay, so here you just need to see that 1, 2, and 3 are three distinct values, and you can consider them as three candidates. Those have stood up for any election. And how many times 1 has occurred? 1 has occurred 3 times. Thus, you can say that 1 has got 3 votes. 2 has occurred 2 times, 2 has got 2 votes, 3 has occurred 2 times, that means 3 has got 2 votes. So now I hope that you get the language of this question, right? Let's move ahead to the sample test case so that we can start understanding the question with even more clarity. So here's this first sample test case. In this, you can say you have 2, 2, 3, 1, 3, 2, 1, 1. Now we need to find out of all of these candidates who have won, and we are actually not considering just one person or one candidate, but what we are considering is how many of the candidates have got the majority vote. And what is the deciding factor of majority vote? We are saying that if n votes were given, out of those, if any of the candidates have got more than n by 3 votes, we can consider them as majority elements. All right, what is n here? Number of votes, and that is equivalent to the length of your array. Cool. So in this case, if we have to proceed with this one, you can say we have 3 candidates again, 1, 2, and 3. The n given here is 8. So what will be n by 3? 8 by 3 is going to be your 2 for that matter. Now, the thing is, if you start counting up the votes, how many times 1 has occurred? 1 has occurred 3 times. For 2, 2 also have occurred 3 times. 3 has occurred 2 times. Okay, so these are the candidates, and below written are the votes that they have gotten. Now, out of all of the candidates, which are the majority? This one and this one, because it is bigger than 2, the value n by 3, right? So in this case, that is what we are doing here. We are returning these 2 elements as an answer. And once we are doing that, just because the question says, we need to arrange them first in an ascending order, and then we have to return it in the form of answer. Okay, got this point? Seeing 2 more examples here, you can see in this case, you have your 2 elements. First element, or you can say the candidate is -5. Another candidate is 3. -5 occurs 2 times, 3 occurs 1 time. The value of n here is 3. That means 3 by 3 is going to be 1. Any element has to occur more than 1 time to be considered as a majority element. So -5 is occurring more than 1 time. Thus, this is the answer. The last case, you can see 1, 2, 3, 4. 4 candidates being there. 1 has got 1 vote, 2 has got 2 votes, 3 has got 1 vote, and 4 has got 2 votes. Okay. What is the deciding factor? N is 6. And if you do 6 by 3, you get 2. So for any element or any candidate to be considered in majority, it must get more than 2 votes. But none of the elements here is getting more than 2 votes. So we have to return an empty array in such case. Now I guess you completely have understood the question, and we can move ahead to start forming the approaches of it. But one more observation I would like you to make before we are moving ahead for the approaches is, let's consider one more case of n by 2. I'm giving a slight variation to you. Let's suppose you have this array, and we have a few candidates in it, and you are considering any element or any candidate as majority candidate if it has got more than n by 2 votes. Now think very intuitively. If half of the votes are occupied by one candidate and even one more vote, so that it can be more than n by 2, what do you think that how many majority element can exist in such case if you're talking about n by 2? Well, the answer would be 1. Why? Because just for the leftover array, there is not much space left for any element to occur more than n by 2 times, right? So in this case, when we are talking about, or when we are saying that Okay, I'm going to consider an element as majority if if the votes go beyond n by 2. In that case, only one element can be considered as a majority element. Okay. Moving ahead to the case that we have of n by 3. Let's again take the same example. Now, if I just, let's say, break it in three parts, right? These are three equal parts. That means this is n by 3, n by 3, n by 3. Now, any element, for it to be considered a majority element, it needs more than n by 3 votes. So consider it has got more than n by 3, it has got more than n by 3. Do we have enough space left for any more element? No, right? So in our case, when we are having n by 3, the maximum number of majority elements that we can get is going to be 2. Okay. Well, actually, this is a pattern. If you see it closely, whenever we are considering any element as majority, and we are saying that, okay, if it is if it is more than n by k, then we can consider that a majority. Then there are possibilities of k minus 1 majority elements in the array at most. Now that you have realized that we can either have one, like we can either have 0, or we can have 1, or we can have 2 majority element in our case. That means of n by 3. Now we can move ahead and start forming the approaches. Let's move to the very first approach, or the brute force approach that you can make. So for that, considering one sample example, in the very first thinking approach, what you can do is you can simply start traversing your array from this point. And let's suppose you picked up 2. You picked up 2. Now what you can do is you can move, like once you have seen 2, that means it has occurred for one time already. Correct? It has occurred for one time. Now you can move from this point till the end. You can run a nested loop. Let's call it this one I and this one j. You can run a jth loop from this point to this point, and every time you are encountering 2, what you can do is you can start adding 1 to it. Eventually, once you have taken one complete traversal or one complete iteration of it, you would have the count of 2, right? Once you have the count of 2, then you can measure that the count or the number of votes that 2 have got, whether we can see or whether we can say that 2 is a majority element or not. In our case, n is equals to 8. So here we know that if we do 8 by 3, we are going to get 2, the number of votes that 2 has received. So here what is going to happen? We can consider 2 as our majority element. So what I can do here is I can create an empty array and I can name it result, which would store the results that I am going to generate here during the traversal. So once I've received this, the format would be something like this. You have your for ith loop. Okay. Inside that, you would have your for jth loop. Your I is going to go from 0 till n minus 1. Every time your j is going to go from I plus 1 to n minus 1. And every time this is happening, what you're going to do is you're going to complete your count. And once you have counted, you're going to check it here that whether this is a majority element or not. If this is a majority element, then what will you do? You will append your answer, or you will add your answer there in the result list. So for this time, we can add 2 here. Now going on ahead, moving to this point, I can see, okay, 2 is actually for the next time, and I already have that in my result. So moving ahead once more, I can see 1. Now 1 would again be like this. I can say, okay, 1 has occurred for the first time. Let's give let's give 1 vote. And then from this point to this point, again, I have to travel. I have to find the count of 1. I have to see whether it is majority element or not. In our case, it will be a majority element because it has received 3 votes. So we can add that there in the result array as well. So if you consider this result array, you would have these 2 values so far. Then going on for 3, right? For 3 also, you would only have 2. It would not be included in our result array. Eventually, you would create this result array. You can see because 2 appeared first, in my case, this is a possibility, and we don't want to return the answer just yet. We first need to arrange them in increasing order. So if I see that, okay, my first element is bigger, I would simply arrange it like this, and then I can return my answer. Now, what complexity would it take? How much complex would it be in terms of time and space, this approach? For sure, we are using a nested looping here, okay, and I have to perform order of n operation of j order of n times for my I, correct? So this is going to be order of n square in terms of time. Now, am I using any extra auxiliary space? Well, not actually. It is just the result that I'm calculating, but without considering that, for my approach, I'm not using any extra memory, right? So, okay, I can say that it is going to be order of 1 in that case. But this sure isn't the best way to do this question, right? We cannot have this big complexity because the question doesn't require it. So we need to make a little optimization to it. How can we do that? Well, if I just go on with the basic method that if we want to reduce the time complexity, we must use some extra space or any extra data structure to manage our data well. For that, the best thing is hash maps because now we are thinking about counts and we are talking about frequency. The best data structure to maintain track of the frequencies and the count is a hash map or a dictionary. So now let's say how we can deal with the same question and we can improve it when we use a hash map. Let me just take up the sample test case. Okay, considering this here, my main motive around the hash map is to create a frequency chart using it. What is a frequency chart? Well, a frequency chart is, you can say, it would have all of your elements like this, and corresponding to that, it would have how many times it has occurred. So 2 has occurred 3 times, it would have it like this. 1 has occurred 3 times, 3 has occurred 2 times. It would have it would be like this. And once we have generated the frequency chart, we can again do the like usual method, checking each and every element. If it is more than n by 3, we can consider that as the result array, and we can return the result array after just seeing whether it is in ascending order or not. Quite simple. So my main focus is just to generate this frequency chart using my hash map. What will I do? I will have an empty hash map initially here. Now I would start traversing my array from this point to this point. Let's again call it ith loop. Every ith element that I have to check whether this ith element is present in my dictionary or in my hash map or not as a key. Initially, it is empty. That means it is not present. So if that is the case, what will I do? I would simply make this element as a key and I would give 1 as a corresponding value to it. Okay, that signifies that, okay, 2 has occurred for 1 time now. Now going on ahead, once I take one more step here, I can see, okay, 2 is now occurring for the second time. Now if I check whether this ith element exists in my dictionary or not, well, this time it does. So what decision am I making? I'm making whether this exists or this does not exist in my hash map. Okay, so if it does, that means we need to just increase the count of the already existing value. If it does not exist, then that means that we need to create a key and we need to give the corresponding value. Otherwise, we can just add 1 to it, right? These are the two cases. So in this, that we have gotten this 2 for the next time, I'm just going to add 1 to the existing value. Now I encountered 1. Is my ith element present? Well, actually, it does not exist. Create up a new key, give the corresponding value 1. 3. Is it present? It is not present. Create up a new key, give the corresponding value 1. 3. Already existing, add 1 to it. 1. Existing, add 1 to it, add 1 to it, and eventually you have 2, add 1 to this one. So once it's calculated, you would have your frequency chart like this. You would have a frequency chart like this. Now, once you have it already, you again just need to go through all of the values that are present in your hash map or the frequency chart, and you just need to check that all the elements which have the count of or the votes, if you want to say it like that, more than n by 3, you're going to store them in the result and you can simply return the answer as we have already seen in the previous approach. It's simple. Analyzing the complexity that this approach might have. Talking about the time complexity. How many times are we iterating this array? Are we doing any redundant work? We are not. We are simply starting up from here and we are ending like at the end of this array. So we are just going from 0 to n minus 1. That means we are just taking order of n time for this approach. Is this the only operation? No, not exactly. This operation is to create up your hash map or create up a frequency chart. Now, in the worst case, it could be like all of the elements are unique and you have your this hash map as big as your array. And once you're going on checking for the elements which are majority, you again have to travel for order of n. So it is going to be order of n plus order of n, which can be considered order of n only, right? But you just need to realize that what is the internal working. Now talking about the space complexity. This is in the terms of time complexity done. Talking about the space complexity. Well, now space complexity is actually order of n here. How and why? Well, we are creating up a hash map. Again, I just talked about the worst case of it. We can have all the unique elements. So my hash map can go as big as my array in length, right? It can have n values there. It can have n keys there. So that is the thing. My auxiliary space that I'm using is growing with n. That means order of n is going to be the space complexity for this approach. Now what we have done, from n square, we have brought down our time complexity order of n, but from order of 1, the constant time complexity that we had in the previous approach, now we actually have got that to order of n, which is not very favorable, right? We can think a little more. We can try to apply a few algorithms to that, which is actually going to bring our solution to order of n without taking any extra space. And that is what my next approach is going to be all about. Okay, let's move ahead to that. But before moving ahead to that, let's discuss the code of this approach as well. Okay, coming back to here, we can see the code here. I have declared kept the track of n. I have made a dictionary, or you can say a hash map here, named, and I have named it as frequency. Simply, the name is pretty elaborative. And I have taken a result array or result list, which I'm going to be using to store my results. Here, these two lines are responsible for creating up your complete frequency chart. A little intel about the this function, if you're not familiar with the syntax. Well, in Python, what get does is, this line is written here, right? So when you are saying your hash map or your dictionary dot get, it searches your dictionary and whatsoever key is present. Okay, you're saying get the element. That means if element key is present, the value corresponding to that is going to be fetched here. But if that is not, then the second value that you give after the comma is like this acts as a default value. So if the key is not present there, instead of an error, you would get this value here. So these two lines, if so ever you are not getting the element, okay, then you would get a 0, you would add 1 to it, and in turn what will happen, a new key would be created with value 1. Just I have already told you in the approach, right? And every time you have the key already, that element's value is going to be there, and you can add 1 to it. Quite simple. The hash map created here. Now what are these lines doing? Well, we are iterating through all of the items of the frequency chart that I have, and I'm seeing that every count that I take up, if that is greater than n by 3, if that is so, then I'm just simply appending it to my result, adding it to my result array. Once that is done, in these two lines, I'm just checking, okay, whether these are in increasing order or not. If these are not, then I'm going to put that in the increasing order. As simple as that. After that, I can just return the result array, and this approach would be done. Now, once we're done with this one, you have completely understood it. Let's move ahead to an even better approach. Okay, discussing this algorithm, like this approach, it is based on Moore's voting algorithm. But before going on to the case that we have of n by 3, I would like to make you understand that how this algorithm works for n by 2 elements. Okay, that means when we are considering majority elements, if those appear more than n by 2 times in my array. So this algorithm says that okay, based on the fact that we have already realized that when n by 2 is the case, we can only have one majority element. When n by 3 is the case, we can only have two majority elements. When n by k is the case, we can only have k minus 1 majority elements. Based on this fact, this algorithm does not actually count the votes, but it counts the chances of an element to be a majority element. How this algorithm goes? We take up two variables. Okay, first variable, you can call it as a candidate or element, whatsoever you want to, but that is going to be any person we are picking if you are going in the context of an election. Now, another variable that we need to keep track of is going to be the count, or you can say votes. Now, this count of votes is not going to be the actual count or the number of votes that any of the candidates have got, but it is going to be the chances that the current candidate might have of winning. So how does this algorithm begin? Well, initially we say, okay, there is no candidate and there are no votes. -1 just to represent, okay, there is no candidate. 0, all right, initially there are 0 votes. Now everything is based on a few decisions. Let's say, what count do we have, or what vote do we have? If I have count as 0, okay, that means no vote. It signifies that it is the time that we select up our candidate. Okay, the moment you have your count as 0, what do? You update the candidate. So here, initially for us, if you are just starting to move in this array, I just saw that, okay, my count is 0. If the count is 0, I would update my candidate. Currently, the element that I have here is, this element is 2. So I would update this with 2. Now I'm considering 2 as my possible candidate, which can turn out to be a majority element. Now once I have this, the count will also increase by 1, or the vote will increase by 1. Okay, 2 has occurred for the one time. It is signifying that. Moving ahead in the same direction, this time you can see the count is not 0, it is 1, or like it is any other value. Let's call it the else condition for count. Okay, if this is happening, then what do we need to do? Then we need to make another check, that whether the element that I have, the ith element that I have, if that is equals to my candidate or not. If that is equals to my candidate, then what will I do? I would simply increase the count. Okay, but if that is not equal to my candidate, I would decrease the count. This is the special thing about this algorithm. We are not just keeping the count or the track of number of votes. We are saying that, okay, if a new candidate is being appeared or a new candidate is getting a vote, that means it is lowering down the chances of the previous candidate. Okay, and one new vote or one different vote means one vote less, or you can think of it at one chances left less for the previous candidate to win. Okay, going ahead with this approach, I saw 1. It falls in this category. I'm going to make it 0. Correct? 1 minus 1, 0. Now for the next thing, this time my count is 0. I'm going to fall into this place. That means I have to update my candidate. I am going to update this candidate here. Now 1 is going to be my new possible winning candidate. Okay, moving ahead in the same direction, I found 1 again. I would fall in this category. Count has some value and candidate is equal to the element is equal to the current candidate. I'm going to increase the value. So it is going to keep on increasing. First increase this one, another increase this one. Then one more time it is going to increase because the case is same. The moment you encounter this value, which is a different element, not equal to candidate, we are going to reduce this value here. Okay, 5, again, different element, not same to the current candidate that I am having. I'm going to reduce the value. 1 appeared, which is equal to my candidate. Current candidate is still 1. I'm going to increase the value. 1 appeared again. I'm going to increase the value. Okay, now 2 appeared. I'm going to decrease the value by 1. So you can see, following this little chart, I have traversed my complete array. I've traversed my complete array. Eventually, the last standing candidate is 1. The last standing candidate is 1 here. This count or the votes that I have calculated, it is of its magnitude does not have any significance. Okay, but the current candidate which is standing till the last, it means that this is a possible majority candidate. We were checking for n by 2. Now I've got this possibility. So I need to now check that how many times 1 has occurred. Now I will count the vote of 1. I will count the votes of 1. Because 1 has the possibility that it can be majority element and no other element has the possibility. So we're just checking one possible element. Okay, if this is majority element, then okay, all right, you got your answer. But if this is not, then you do not have any majority element in your array. As simple as that. So 1 has occurred 1, 2, 3, 4, 5, 6 times. All right, and how long is this array? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is 10, the number of elements is 10. You have n equals 10, n by 2 is going to be 5, and 1 has occurred for 6 times. That means, all right, 1 for this case is our majority element. Okay, now I hope you are clear with Moore's voting algorithm. Now the thing is that this actually is not our question. Our question revolves around n by 3. Now the time is to modify this approach a little. What do we know about n by 3? How many possible majority elements can be there? 2, right? Written here. So for that, once we know that, okay, there could be 2 possible candidates, so why not we have 2 variables for us? Let's call them, okay, just let me give the name as element 1 and element 2. In these 2 variables, I would start finding out which can be my possible 2 elements or 2 candidates which can turn out to be as majority elements. Okay, for that, just like in the previous case, I was having another variable to keep the track of votes or chances of winning. For that, I will have 2 variables here as well. Let's call them count 1 and count 2. Count 1 will be keeping the track of element 1. Count 2 will be keeping the track of element 2. Initially, we do not know any element. Initially, we don't have any count. So both of the elements, let's call them -1, and both of the counts are going to be 0. Now you know how the thing goes. If you know that your ith element is equal to a candidate, then what happens? The count increases. If ith element is not equal to the candidate, the count decreases. The thing is, now we have two elements. How are we going to compare? Simply, let's say we have this ith value. Firstly, we are going to compare it with our element 1. If this ith value 2 is equal to the current element 1 or the current candidate 1, it's fine. I can increase the corresponding counter. If this value would have been equal to the candidate 2, after checking this one, I come to element 2. If the candidate is equals to element 2, then I can increase this counter. But third condition could be this value is completely different. Okay, this value is completely different. If in that case, we are going to reduce the values of both. Sorry, not here. Reduce the values of both of the counts. But before checking for this condition, that means before checking for that, okay, this element is not equal to both of our candidates, we need to check one more thing. Before decreasing a count, we need to check one more thing. Are our counts, both of the counts, if any of the count is becoming 0, that means what is the time? The time is to update the candidate. Okay, so firstly, I'll check element 1. If it is equal to my candidate, my count 1 will increase. Nextly, I would check, if my ith value is equal to my element 2, I would increase the counter 2. But the third time I would check that, all right, whether my count 1 is 0 or not. Like if my count 1 is 0, then my element 1 would be updated. If my count 2 is 0, my element 2 would be updated. If the ith value that I have, it is completely new and does not matches both of the candidates, and I still have votes in both of the count 1 and count 2, and that means I have to reduce both of the count 1 and count 2 by 1. Now, eventually, once I go through this array completely, then I can find out two possible values, which can be our majority elements. Let's try to see these values and try to run this algorithm here in this example. Just by seeing at the question, you can see that how many elements would you be getting. Let's begin. Initially, my element 1 is -1, my element 2 is -2, and my count 1 and count 2 are 0 and 0. I got 2. I compared it with my candidate. Is it equal? It is not. I compared it with this element 2, not equal. Now I saw if my counter 1 is 0. Well, yes, it is. Then I would update this as the ith value. And once I update that, the count also increases by 1. Make sure of that. Now, once this iteration is done, this step is done, going to the next element. Now I have 1. Checking my element 1 here. Can the candidate is not same? Count 1 can will not increase right away. I would check the element 2. Whether these two things are same? No, these two things are not same. Now I check whether my count 1 is 0. It is not 0. Whether my count 2 is 0? Well, yes, it is. This is 0. That means I need to update my element 2 now. Now my element 2 would be updated as 1. Okay, my element 2 is now updated as element 1. My ith element, this one. All right. Now, again, moving ahead in the same direction, I have this element here. I'll see whether it is equal to element 1. Well, no. Is it equal to element 2? Yes, it is. My counter would increase to 2 because now for the second time it has occurred. One more 1, my counter will increase to 3. One more 1, this counter will increase to 4. Right? This counter will increase to 4 because so far I did not see any change. But this time, what happens? I have 3. Is it equal to element 1? No, it is not. Is it equal to element 2? It isn't. Is any of my count 0? None of my count is 0. Then I will reduce both of the values by 1. This will now become 0. This will become 3. Now I have another element, the element 5. Here, I will now check element 1, whether it is equal to my current element, the ith element? No. Is it equal to my element 2? No. Now, do I have any of the count as 0? Well, yes, I do. And in this case, what will happen? This will be updated. Once this is updated, I'll go ahead and mark its count as 1. I encountered 1 here. Then element 2 is going to increase, right? I encountered one more 1. Element 2 is going to increase one more time. Now I encountered 2. In this case, what happens? You can see it is not equal to my element 1, not equal to my element 2. Both of the counts are not 0. That means both of the value will reduce. This will become 0. This will become 4. My iteration has ended. The last two standing candidates are 5 and 1. Out of these two, or these both can be my majority elements. Either of one can be my majority element, or none of these two can be my majority element. For that, I'll count how many times 5 has occurred. Well, 5 has occurred only one time. How many times 1 has occurred? 1 has occurred 6 times. I can see that 1 passes the criteria of n by 3. So I can say, all right, 1 is the majority element for this one. Okay. Now, I hope now you understand how we are managing two values parallelly, right? Let's quickly see the code for it so that everything can be completely clear to you. Here we have the code for it. You can see here I'm keeping the track of n. I have made two of my elements here, initializing it with -1. I have the corresponding counts initialized with 0 and 0, 0. Then all the conditions we have been talking so far. We have been talking about so far. Every element that I pick up, I'll check it with the element 1 I have. If that is so, I would increase its count, the corresponding count 1. If that is not the case, if my element 2 is equal to the element, then I would increase the counter 2, which is the corresponding counter. If this is not the case and my counter 1 is available, or you can say my counter 1 is 0, I can update my element 1 and I can make its count as 1. Okay. If my count 2 is 0, that means I have to update my element 2 and I have to mark the corresponding count 2 as 1. Now, if that is not the case, apart from all of these, the only case is that the element 1 that you have, the element 2 that you have, both of the elements are something else than your ith value, and both of the counters are not 0. In that case, you will reduce the value of count 1 and count 2 both, okay, by 1. Now, once this loop is successfully executed, you have clearly seen how element 1 and element 2 may contain our possible majority elements here. Okay, so here's the result, and I have just updated these two counts so that I can now find whether my two possible candidates are for sure the majority elements. I've got the counts of both. I've compared the counts. If those are bigger than n by 3, then what will I do? I would append those to my result, and here I've checked that whether these are arranged in increasing order or not. If it is not, I will just swap them, and then I would return the result from here. Okay, and this would complete my approach and as well as this question. Quickly, let's discuss what is going to be the complexity of this approach. What are we doing here? We are simply traversing, with this loop you can see, we are simply traversing my complete array once. That means order of n. And after that, I just have to count the occurrences for at max 2 value. So I can have plus order of n, not like nothing more than that. So eventually it is going to be counted as order of n only. Right? So I can say the time complexity that I have for this approach is order of n. Am I using an extra space? We are using just the variables, which is not counted, correct? So the space complexity that I have for it is going to be order of 1. So I hope now this approach is completely clear to you. Let's quickly go to the coding window and try to run this program so that we can see if it is passing all of the test cases. All right, let's compile this. Okay, so it is giving us the expected output for this one. Let's try to submit that and test it against all of the test cases. Okay, so this program has managed to pass all of the test cases here. Now, I hope you have got this, like all of the approaches that we have discussed. Now you understand this question well. If you have liked the video, if you liked the solution, then do let me know. And again, as I always say, take a few examples up and try to write in the code if you have any difficulty. Okay, thank you.